So hello everyone, Assalamu alaikum. How do I make this? So my name is Momo Arai, and I'll be teaching the first part of this lecture, which is Hemodynamics 1. Now, this lecture is like there's a lot of math and there's a lot of formulas in the lecture, but I'll try to make it easy and like as simple as possible for you guys so that you can remember that in the exam. So I'll start. So this is the first slide that he has in the lecture. And I don't want you, I know there's a lot of things going and there's a lot of formulas, but I don't want you to get overwhelmed because he explains all of this in the slides that's coming up. And it's in hemodynamics, like both of the lectures together has all these formulas. So we'll skip this for now. Okay, so as you know, like the heart is a pump that heart is a pump that pumps blood to all the body, and there's two separate circulations. What I mean by that is that so if you see this picture, you'll get to know more about it. So we have, so we have the pulmonary circuit and the systemic one. So there's a circuit that goes and supplies only to the lungs, and then there's one separate one that goes and supplies to the rest of the body. So now, like as you know, I'll just go over it really quickly so you have a main idea. So you guys know that there's the right side of the heart and the left side of the heart, and the left side basically it receives all the oxygen from the body, and they're all deprived of oxygen. So because they're already used up. Okay, and then it goes from the right atrium to the right ventricle, and it goes all the way to the lungs. Now then it carries oxygen from the lungs from the air we breathe in, and then it gets oxygenated, and then it goes back to the heart. Now this circuit is called pulmonary circuit, and then when it goes from the heart to the rest of the body, it's called systemic circuit. The reason this was brought up was because it was just to show you that both sides of the heart, they pump the same amount of blood or the same volume of blood. Okay, but the only difference is the pressure. So as you may know, like the pumping to the rest of the body takes much more work than pumping only to the lungs, right? So you want to build that pressure, and that pressure is built up by the walls of the left ventricle, and that's why you get it's more forceful, and it's able to go all the way around our body really quickly. This is all simple, right? So I'll move on to the next slide. Now, hemodynamics has a lot of parameters, and there's a lot of things. When you think about blood vessels, for example, there's a lot of factors that come into play that affects things like flow, resistance, and we'll go over them slowly. So the first, I'll try to go over them individually and try to explain something that you might not understand. So the first one says diameter. Diameter is just how, you guys know what diameter is. It's like how wide the blood vessel is. Then we have blood flow velocity. Now velocity is just how fast the blood is. And then total cross-sectional area takes, so blood vessels, we'll consider blood vessels as being circles. So the basic formula for the area of a circle is pi r squared. Right? Wait, by the way, if you guys have any questions, feel free to stop me. I forgot to say that.
Can you repeat point number one, individual blood vessel?
Oh, okay, yeah, sure. I'll just erase this. Okay. Do you guys have any questions before this? I just went over the basics. Is it okay? So I'll go over the first one again. So let's take a blood vessel. We'll take it as a circle. Okay. Now the first parameter of a blood vessel is the diameter. Now diameter just means how wide a blood vessel is. So that technically means that it's from one end of the vessel to the other end. This is what we'll call a diameter. Is that fine?
Yes, thank you so much.
Okay, and then we'll see a lot of formulas that have radius in them. So for those of you who don't know, radius is the half of a diameter. So we'll call this part, so this whole thing is diameter, right? But a half of the diameter is called radius. So we'll call that radius of the blood vessel, because this is important, because this will come up in formulas. Okay, now that's the first one. Second one is velocity. So velocity is another word for like how fast blood flows through a blood vessel. And velocity, it just means that how fast the blood goes. Usually we do like distance over time, how like the speed of the blood through a blood vessel. And then the third one is total cross-sectional area. So remember how we said this is the radius? Area just means, so you'll have a formula for that. And for area of a circle, we usually do pi r squared. So pi is a constant value, it's like 3.14, so it always remains the same. However, like radius changes, right? So this part always changes. Now, let's say, so for example, this is important when you have like a small blood vessel or big blood vessel, and you want to calculate the area of that blood vessel. So the smaller the radius, the smaller the blood vessel is, the smaller the area. Is that clear?
Yes, thank you.
Okay, you can write in the chat too. Oh, I just saw. Okay. And the bigger the blood vessel, the bigger the area. And that's it for area. So total cross-sectional area means it takes all of all of these vessels area into account, and they just add it up together. Now the fourth one is blood volume distribution. From the name, you can tell like this just means how the blood is distributed across the blood vessels. So I'll come to it later on, but does that make sense? You just want to know like where the volume of blood mainly is, and like how it flows through the body. I'll move on unless you guys have any questions. So, okay. So the fifth one, total peripheral resistance. This is an important concept because resistance basically means like the force that's pushing against your blood flow. So let's say you have a vessel, right? There's blood flowing through it, and the force that's exerting against it, or that's like against this blood flow, is called resistance. Now, resistance can be changed, resistance can be affected by a lot of factors. Let's say the walls are like thicker, they're made up of more collagen and elastin. That's when you have more resistance. And then let's say you have a narrow blood vessel, you have a wide blood vessel. That's when resistance also changes. Okay, I'll explain more about it, but I just want you to know that resistance is the force that pushes against the blood flow. Okay, so it affects flow of the blood, and it comes up in other formulas. So that's resistance. Now the sixth one is mean blood pressure. Now blood pressure, you guys know, like how do I explain? It's just the amount of
It's basically like the amount of pressure that the movement of blood across the vessels is applying to the actual structure of the blood vessel.
And it's I'm sorry.
No, it's fine.
Do you guys get that? Like these are just the parameters. I'll go over them again, but I just want you to know the definitions for now. Is that fine? Okay. And blood, I think okay, fine. So blood pressure is something you can measure, and that's it. I'll go to the next one, and it will make sense as I go on, so don't worry about this. Oops. I'm sorry.
The last. About blood pressure.
Blood pressure. Okay, so blood pressure is, so you know how the blood is flowing through the vessels? It creates like this pressure against the vessels, and it's something you can measure. So the normal blood pressure, like for all of us, is like 120/80, like that. Do you get that? Okay. It's just a measurement. Wait, I can't move it. Just a second. I can't move the slide. Sorry.
What's happening?
Okay, wait, I'll just move on to the next one.
Technical difficulties. What is going on? I'm sorry, we're prolonging the report.
Yeah, I'm sorry. I'm really sorry.
Okay, wait, this should work. There we go.
So thank you. So we'll Okay, so we'll go over them really quickly again. So diameter, like I said, it's how big the blood vessel is. Now you have from the heart, you have the largest arteries that carries like all the blood and all this pressure inside them, and they're like the biggest blood vessels at the beginning. And then when this goes throughout the body, it will start branching up into capillaries, which they're important for nutrient and oxygen exchange. And the reason they branch is so that they can have like thinner walls for the oxygen and the nutrient to pass through. And this is what we have all throughout our body. And then they join back together. They join back together into what we call the venous system. So now they're venules, and then they like join into great veins, which go back to the body through the heart. And that's the first diagram I showed you. So all of this gets collected together, deoxygenated blood, and it goes back to the heart. So the cycle is repeated again. Okay, so the diameter here, it's like bigger on the artery side, and then when it goes to the capillaries, it becomes smaller and smaller, right? So that's why the diameter here, the values are shown here. They're very small, and then when they branch up again together, they become really like big again. Okay, that's for diameter. For velocity, you can see the values here. So it would make sense that having greater speed, or like the blood is rushing through very quickly in bigger arteries because there's more blood, right? When the when the vessels become smaller and smaller in the capillaries, the blood starts to like slow down, so for the nutrients and the oxygen to pass through again. And then when they branch up into like veins, they become bigger, like the speed is faster. So nothing. So can you still hear me?
Can I change the mic? I'm sorry, I put my earphone.
Yes, we can still hear you.
And then so I just wanted to say, like, you don't need to memorize any of this, like you don't need to memorize the values, but I want you to understand how the diameter changes. So the diameter and the velocity, which is the speed of the blood, it slows down in the capillaries, or it gets smaller in the capillaries. That's all I want you to know. Okay, is that clear? Because I'll move on to the next one. Okay, so now even though we said the capillaries are the smallest part of the whole, like the blood system, when you calculate the cross-sectional area of all of them and add it all together, they're the largest of the whole system. And I'll explain why. Because even though they're like all of them are really small, and when the radius of them is really small as well, and when you calculate the area of each individual like vessel, you'll get a very small value. But when you add all of these branches together, all of these areas together, you'll get a very large value. And it's capillaries have the largest total cross-sectional area. And if you get a question like that,
Do they understand that?
do you guys get that part? Like, do you know why it's the biggest? Because you're adding all of the branches together. Okay. We'll keep on repeating this, so don't worry about it if anyone has questions. No, like I was saying, if it comes in a question, you can which has the greatest total cross-sectional area, the answer is capillaries. And again, it's because there's a lot of branches that you add together, unlike, for example, arteries or vein, where it's only one. Okay, so let's go on to blood volume distribution. So like I said, this just means how the blood is distributed across the vessels. Now, as you can see, the largest, like the greatest amount of volume is in the veins. So this is the venous system, it's in blue, and these are the arteries, so it goes from here to here. And the largest amount is in the veins. Now, you might wonder why. There's like two reasons for it. So the first reason is, we'll come to it in the second lecture, there's something called compliance. But basically veins can hold a lot of blood at one time. The second thing is like the vessel walls are very thin, and they can kind of like take in that all of that blood volume, you know. So the arteries, they have thicker walls because they have a larger pressure from the heart because it's just exiting out of the heart, right? And they have a lot of pressure, but it flows quickly through. And then when it goes to the capillaries and when it joins up into the veins, they kind of like slow down and they go slowly through to the back to go back to the heart. Does that make sense? And this will be explained later on too. Okay, I'll repeat. So again, this just means how much the blood is in a vessel, for example. But if they ask you which vessel has the greatest or the biggest blood volume, like the amount of blood, you would say the venous system, or a lot of blood will be in the veins. So again, the arteries here, they're under high pressure from the heart, and they're just trying to like push the blood through to the rest of the body, right? But the total volume of blood, all of this has it's the same amount of blood going through, but it's just how much blood there is at one time. So there would be less amount of blood compared to the veins. So the veins would hold the largest amount of blood. It's like a pool of blood, okay? It still goes back to the heart, but it's just going slowly. It can hold a lot more. The vessel walls are very, very thin, and it can like expand to hold that amount.
We'll talk about
Yeah, we'll talk about this later. There's something called compliance. You'll get more from there. Is that fine? Or if you want me to repeat, I don't mind. Like I can repeat again. Okay. So I'll move on. And if you have any questions again, when it's repeated about the compliance part, we can repeat. So this is a summary of everything I said so far. So again, these are the parameters of a blood vessel. Okay, the first one is diameter. Diameter, again, it's the smallest in the capillaries, because as you can imagine, the capillaries are the smallest, like they're the narrowest part of the blood vessel. Okay, and then when they branch up again, they join up again, they form the veins, and the diameter, like the blood vessel, gets bigger. So diameter is bigger. So for the second figure, it's total cross-sectional area. And like I said, which vessel has the greatest total cross-sectional area again?
Capillaries.
Yeah, capillaries. Okay. And then when you go to C, it says blood pressure. So I mentioned it during the last parameter I was discussing. The blood pressure decreases as you go along. So the aorta and the big arteries that exit from the heart, they have the greatest amount of blood pressure. Okay. That's because, again, it's just coming out of the heart with all the spores, so they have the highest amount of pressure. But when you go, when it goes to capillaries and when it goes to veins, it again slows down. It has less pressure effect on the blood vessel. It stops pushing on it as hardly as before, so it decreases with time. Is that fine? So the blood pressure decreases across. Okay, and then when we go to velocity of blood flow, that's just how the speed changes throughout the blood vessels. So the speed of the blood would, again, it would go a lot faster in the arteries, and then it would slow down when it comes to the veins. And that's why it also pulls up in the veins, and that's why they have the largest volume like the largest amount of blood at one time. Okay, is that fine? Again, that's all for this slide. It's just a summary. Okay, so I'll move on to the next one. Okay, so now the formulas will be starting from now, but inshallah it will be like easier, and I'll go through it one by one. So the first one is something called, I'll start with the law. There's something called Laplace's law. Okay, and it says this, and I'll explain again all over. But Laplace is the correlating like the formula with the name is really important in exams, because they can give you the formula or they can give you the name, and they can ask you which one is the right formula, what's the name of this formula. Okay, that's why I'm trying to emphasize on that. So this formula basically calculates the tension that the blood creates on the blood vessel. Okay, So the tension of the tension that the blood creates on the blood vessel, it can be it can be affected by the pressure itself or the radius. Okay, so PI and PO, it just means, so you want the difference in pressure, and PI is the pressure that's pressing on the blood vessel and like trying to stretch the vessel, and PO is the pressure that's compressing the vessel. And is that making sense? Like, yeah, huh?
Since you think of I as inside, O
Yeah.
as outside.
You can say that if you want. Yeah, internal and external pressure.
Yeah.
So there's two pressures acting against each other, and that keeps the blood vessel there. So there's the blood that's pushing against it, that's PI, internal, and then outer or external is from the outside, PO. And that tries to keep the blood pressure, the blood in the blood vessel. So the pressure difference across the blood vessel is, you would subtract them both, right? And you would get the pressure difference. And then after you get that value, you would multiply it by the radius. Now the radius, or like how big the blood vessel is, affects tension as well. And with increase, like the bigger the blood vessel is, the higher the tension. Okay, because it's like the force is distributed across all the walls. Okay. So from what I said, the greater the radius, the greater the tension would be on the blood vessel, right? So which vessel has the greatest wall tension? If you think about it, which one has the greatest? Yeah, okay, wait, why do you say veins? So you would think of the largest. That's
No, keep going. I'm just
yeah. Yeah, greatest, yeah. So I want you to think like that. So the greatest radius, whichever vessels have the greatest radius would have the greatest wall tension on them, right? So veins, yeah, they do work as an answer. Even arteries, like the big arteries like aorta, they would work too. So I want to go back. Wait, I want to go back to the slide which has the diameter. So yeah, since the veins have like the greatest radius, or how it's the widest one, even arteries, by the way, even our aortas, they have the greatest wall. They have a lot of tension. Sorry, I'm trying to figure this out. Okay, so is that part clear? Like, do you guys get the formula? Because that's what I want from this part, from this slide, I mean. So the pressure difference with the radius. Now, pressure difference, you can imagine like the higher the pressure difference is, like the higher the pressure is against the blood vessel, the greater the tension on the blood vessel. Now for radius, I want you to think of a balloon. So whenever you blow on a balloon, it becomes like more stiff with time, right? As you blow air into it. So the greater the radius, the greater the wall tension. Like the wider the balloon becomes, you're putting more force into it. Does that make sense? Okay. So again, can someone say what Laplace's law is, or like the tension, what is it affected by? Two things.
By difference in pressures, like
Yeah.
the pressure compressing the wall and the pressure stretching it,
Yeah,
and the radius of the vessel.
that's all. Good job. So, okay, the way Laplace's law, like the way it's clinically important is when we come to aneurysms. Do you guys know what aneurysm is? Okay, so yeah, aneurysm is basically you have a dilation of the blood vessel. So it can be due to many reasons. You don't need to know that, but it can be due to like the vessel, like the wall being thinner. With age, you get aneurysms because the wall is like, it gets weaker with time. Okay, now due to like, because of this law we just took, when the diameter or when the blood vessel gets wider, you would have a greater radius, right? And with the greater radius, you can see here too. So with the greater radius, the tension would be higher. Okay.
This is not exactly what an aneurysm is.
Oh, I just saw blood clot inside vessel. So no, aneurysm isn't a blood clot inside a vessel. It's more of it's just widening. Yeah.
The weakening.
It's just the weakening of the wall. Yeah.
Causing it to become bigger.
Did you get that? Like whoever said the blood clot. Okay. The blood clots are something else. It's just when like there's like the blood comes together and it blocks the vessel. So that's something else. Aneurysm is just widening. It just gets wider with time. So again, once it gets wider, you have a greater radius. Okay. With greater radius, you'll have a greater tension because as we just took, they're directly proportional. So with the greater tension, it would cause more weakening of the wall, and then you would have a greater, it becomes even wider. So it becomes even weaker with time, and you would get a greater radius again, because of the wall being thinner with more tension. And then with greater radius again, you would get a greater tension. So there's more force being pushed on the blood vessel. Do you get that? So this is like a vicious cycle. Once the blood vessel gets wider, you would get more tension, and then more radius, more like widening, more tension. Is that fine? This is just to explain the concept, by the way. And that's how the law works. If not, it's okay. I can always repeat. I don't mind. Okay, so this the thing here is just showing you how like they treat aneurysms. You don't need to know it, but it's good to know. So they would put like a wire inside to kind of decrease the radius so that blood can flow through normally without creating any tension. Okay. Wait. So that's for Laplace's law. We'll move on to pressure. And we'll talk more about this. So whenever we say, pressure difference came up in the last equation, right? So, but whenever we say blood pressure or mean arterial pressure, mean means average, right? But we have, when we're measuring blood pressure, you have something called systolic pressure and diastolic pressure. And I think this was explained in the previous PAL sessions, but basically systolic, it's a time when the heart contracts, and there's a time when the heart relaxes, and then it creates like a difference in pressure. So you have systolic pressure and diastolic. So whenever you measure blood pressure, for example, you would have the values like 120/80. Whenever they write that, 120 means the systolic, the higher one is systolic, and the lower one is diastolic. Okay, so when calculating the average arterial pressure, which is the mean arterial pressure or MAP, okay, it doesn't work if you take the average of both these values because they're like way different, right? You don't want that. It wouldn't give an accurate answer. So they came up with a formula to calculate the mean arterial pressure and to be fair, like between these two values to get like the middle ground, okay? So this formula, you have to memorize it, but I'll try to like go over it and repeat again and again. So first you would take the diastolic pressure, which is, for example, in this case, 80, fine. And then you would take 1/3 of the difference. So the difference here, the difference in pressure they want here is the difference between systolic pressure and diastolic pressure. So in a way, you're kind of like getting an average of both the systolic and diastolic. Okay, so here 120 minus 80, and then you would get 1/3 of that value. You would divide it by 3, and then add to it the diastolic pressure, the lower end of the pressure. Does that make sense with all of you? Because this is the formula, and you would need that for like other formulas. So whenever they ask you to calculate mean arterial pressure, you would take diastolic plus 1/3 of the pulse pressure. So pulse pressure is another word for saying systolic minus diastolic. It's the pressure difference. Is that okay? Or if you want me to repeat it, I don't mind. Okay, I hope that's clear for everyone. But yeah, that's it from this slide. And I'll explain more and you have questions. So patient has, it's the same number. Patient has a blood pressure of 120/80. What is their mean arterial pressure? But I didn't calculate it in the last one, so you guys can do it and tell me.
That was really fast.
Okay, that was so fast. Okay, yeah. So how did you do it? Like, what's the formula again?
That was insanely quick. MashaAllah.
You can unmute if you want. If it's
I was calculating it as you were explaining.
okay.
Okay.
Yeah, okay. Can you tell us the formula or?
Yeah, it's the diastolic pressure plus the plus 1/3 of the pulse pressure, or systolic pressure minus diastolic pressure.
Yeah. So I hope that's clear for everyone here.
Does everyone understand how she got 93?
Because I was going to write it down now. Okay, you guys got it. Okay, so it's again, like she said, by the way, good job, mashallah. You can, that was so quick. Even I didn't open it. So mean arterial pressure is again diastolic plus 1/3 of the pulse pressure. Pulse pressure again means systolic minus diastolic. So you would have the same numbers I did before. So this is 80, and then this is 1/3 over 120 minus 80. Then when you add that, you'll have a calculator in your exam, right? So you can add that all up, and then you get 93.3 or 93. I hope that's clear for everyone, because this can come in the exam too. It's a very important formula. So this is this is a lot in one slide, but yeah, I'll try to go over it again. So this just shows. So again, like I said, there's pulmonary and systemic circulation, right? And the pressure differs from one place to another. You would have a different systolic or diastolic pressure from one to another. And I don't like how the diagram is like flipped over here, but this is basically the atrium and this is the ventricle, okay? And then the blood goes from here to here, it goes to the lungs, and then it goes back to the left atrium to the left ventricle, and it goes all the way throughout the body. Now, the boxes in green, they just show you what the normal values are. So right atrium, it's the place where it gets all the blood back to the body, right? And that's why it has a very, very low pressure. It's a pressure of 2. It can even go up to like -4 or 0, just so it can kind of like take all the blood. The blood can flow all the way from the body to the right atrium. Okay, and these are all like different values of pressure that you don't have to memorize. I'm just saying, like, it was just shown here to show you how different they are. But for example, they can give you, for example, they'll say calculate the pressure difference in systemic circulation, which is this one, or calculate the pressure difference in pulmonary, which is this one. So let's go from systemic. So the systemic circulation, what they mean by pressure difference is the pressure at the end. Yeah, why is pressure in? Okay, I'll read this and then I'll go. So pressure in right atrium is low. So you know how the heart is, right? Like all the blood comes to the right atrium first, like from the body. So all of it gets back here. Now in like this is basic like physics, but blood or anything would move from something that's of a higher pressure to a lower pressure. So let's say the right atrium is at a lower pressure, like 0, or in this case 2, okay? And obviously the blood in the body has a greater pressure, right? So for the blood to move from the greater pressure to a place that has lower pressure, like since this place has a lower pressure, it would move from the body back to the heart, because it goes from greater pressure to lower pressure. Is that fine? So that's why the right atrium is low. And again, it depends on the place. That's why all of this is different. The pressures are different. But I'll try to go. Okay, I'll try to explain what they mean by pressure difference in systemic and pulmonary. So systemic. So again, it's the pressure difference from the end of that vessel or the destination, or the beginning point minus the destination. or the opposite, it doesn't matter, but you get the idea, right? It's the pressure difference across that whole circulation. So for example, systemic, wait. Okay, so for example, the systemic circulation, where does it reach in the end? So where does the blood flow from all of the body? Where does it go to? Which chamber?
The right atrium.
So right atrium is your end point, right? So you would have right atrium here, and you would subtract the mean systemic arterial pressure from the right atrium. So again, right atrium is the end point. But what's the starting point? What pressure do you subtract it from? You would use the mean systemic arterial pressure, which is the average blood pressure of the rest of the body. So you'll take that as the starting point. Is that clear for everyone? Because I know you might say, like it's like the left ventricle is the starting point, and then it goes to the right atrium. But again, it's the same thing. So the pressure here, it's the same as, oh no, it's not. But you get the idea. The pressure that goes out of the left ventricle is the final pressure, and you would use that. You would calculate the average pressure from all the values we did before as the starting pressure, because basically you're taking the pressure in the whole body minus the end point. Okay, is that clear, or do you want me to explain again? Okay, I'll repeat. So so when you want to calculate, so this equation, the systemic mean arterial pressure that we did before, the map, it's used in these two formulas. So whenever you want to calculate the pressure difference in systemic circulation, systemic, again, it's from the body back to the heart. So you would want to subtract the body's pressure minus the heart's right atrium pressure, because it does go to the right atrium, like it ends up in the right atrium. So what's the pressure of the body? Like we said before, you can't average the two values. You can't average 120 over 80. You want to use mean arterial pressure. So you would take the systolic and the diastolic pressure, and then you would calculate that average. And that's your pressure. That's the body's pressure. Now that's the first point, the starting point, and then you would subtract it from the end point, which is right atrium, in this case 2. So the only thing you're doing here is you're calculating the pressure difference across the circulation. Is that fine? Is that okay? Okay, and if you want me to repeat, I really don't mind. It's okay. So again, the body's pressure minus right atrium pressure. Now, if we do the same for pulmonary, okay, let's go over it. So mean systemic arterial pressure, in this case, they got 93, which we got in the last one. So they're using the normal values of blood pressure, which is 120 over 80. Okay, and that's why they got 93. Now, right atrium pressure, they gave it here, it's 2. So you would use the value of 2, and then you would subtract 93 minus 2, you would get 91. So if they ask you what's the pressure difference in systemic circulation, your answer should be 91. Now let's do the same for pulmonary. Now, so
I have a question.
Yeah, sure.
From where 13?
Which one?
13. 80 plus 13. 13 came from where?
Oh, so okay. Let's go over. Yeah.
I mean 1/3.
Yeah.
Oh.
Okay. So like I said, do you get the formula part? Do you get this part?
Yes.
Okay.
Yes.
So they did the exact same thing. So they did this formula because the number I used is the same in this question. So they did 80 plus 1/3 over times 120 minus 80. Now 120 minus 80 is 40, right? So this would be 80 plus 1/3 of 40, which basically means 80 plus 40 over 3. Does that make sense? Like 40 goes, it's being multiplied, so.
Okay.
Okay, now 40 over 3, wouldn't I need a calculator? Yeah.
13.3.
40 divided by 3 is 13.3.
Yeah, so 40 divided by
yeah.
is 13.3. Is that fine?
Add that
And then
I got it. Yeah.
okay. So add that to 80 and you get 93. So like, as long as you have the formulas and everything, you'll always get the right answer. So for let's do the same for pulmonary again. So you would want the mean pressure in the lungs minus its destination, right? So where does the blood go from the lungs? Where does it end up in? So the blood goes from the heart and then it goes to the lungs. And then which atrium does it end up? This way.
Atrium.
Sorry?
No, not right.
Not right. From the lungs. Okay, so wait, I'll draw it here again.
Yeah, left.
Left, yeah, left. Because from the body, it goes to the right. And then right ventricle, and then it goes to the lungs. The lungs,
Oxygen.
yeah, they get oxygenated there, and then it goes to the left atrium.
Exactly.
Okay. Yeah, left through the pulmonary veins. No, wait, pulmonary. Yeah, pulmonary veins. Yeah,
Section, the one
yeah.
that carries
Right.
oxygenated blood.
Okay, so again, so here you have right ventricle. It goes to the lungs. The lungs through the pulmonary veins goes to the left atrium. So what's the pressure at the left atrium here? You have to note it down. It's 10, right? Again, you don't need to memorize it. They'll be given. So the left atrium pressure is 10. So what's the pressure in the lungs? What's the starting pressure? Okay. So you would do the same thing you did before. You would calculate MAP for pulmonary. That's why they just put mean pulmonary arterial pressure. Now the mean of this is 14. And they got this from this value. So, okay, like I said, they're all different values, the systolic and diastolic, wherever you are, like pulmonary or systemic, right? In the lungs, the systolic is 25, while the diastolic is 8. Now you have two of these values. You can calculate MAP with just these two values. So you would do again diastolic plus 1/3 of the difference between systolic and diastolic. So here it would be 25 minus 8 over 3 because it's 1/3, and you would add it to diastolic, which is 8. So that's what they did here. They did 8 plus 1/3 of 17, which is 25 minus 8, same thing. And then they got 14. Is that clear for everyone? If I'm going too fast, let me know, it's fine. I'll slow down. Okay. So basically what they just did is they calculated the mean arterial pressure from the systolic and the diastolic of the lung, and that's the average lung pressure, you can say. So that's the starting point. The end point would be the left atrial pressure, because that's where the blood will end up from the lungs. So mean pulmonary arterial pressure is 14, left arterial pressure is 10. So 14 minus 10 is 4. So that's how you get the answers. So they're basically like these two are the same. It's just the values are different because you have higher pressure in the systemic throughout the body. Is that fine, or do you want me to repeat one more time? Okay. So this is again, you don't need to memorize it, but this is just to show you like how these values, if you get a blood pressure with the systolic that's like 120 over 120 or 130, that's when you have hypertension or like a high blood pressure, and that's abnormal. So you would normally not have that. Okay, even for diastolic.
What?
So we'll move on to the second concept, which is regulation of blood flow and resistance. Now resistance will come a lot in this part, but before that we'll move on to types of blood flow. So there are many formulas regarding blood flow and how blood flows throughout the vessel, but the main important thing you want to remember is flow is difference in pressure over resistance. Now we're not talking about like circulations, it's just I'm talking about a vessel and the pressure difference from one end of that vessel to the starting point or the other end. Okay, And that's the pressure difference. So you would have pressure at one point minus pressure at the other point, and then you would divide that by resistance. You would get how the flow of the blood is. And then there's two types of flow. I'll talk about them. So the first one is laminar flow, and the second one is turbulent. So laminar means when the blood is flowing like straight through the blood vessel. There's no change in direction. It just goes straight through. And then turbulent is when you have, for example, there's something blocking the blood vessel. You would have a disturbance in that like flow. So it would flow in like circles, it would flow in all directions. So that's what you call turbulent flow. That's the difference in flow, and there's a formula you can calculate it for that. But before that, I want to explain how this came up to be. So pressure difference, like I said, blood will always flow from a greater pressure to a lower pressure, right? So the greater that difference is, the faster the blood will flow. That's why you have flow is pressure difference over resistance. So the greater the pressure is, the numerator, if it's higher, the flow will be higher, which means the blood will be faster. And then whenever there's resistance to that flow, whenever there's a force pushing against that flow, if it's high, you would have the blood would flow less or slower. And that's why it's in the denominator. They're inversely proportional. I hope that makes sense, because the next formula that's coming up is this one. It's called Reynolds number. Okay, and basically what this formula is saying, if you have a low Reynolds number, it means you have a laminar flow. If you have a high Reynolds number, it's turbulent flow. Okay, so you can remember this as like low, having a low with an L, the Reynolds number is laminar with an L, and then having a high one is T, turbulent flow. And I'll again explain how that happens. Is that fine till now? So you have two formulas in this slide. Yeah, they are inversely proportional. RE and resistance with the flow is inversely proportional. Pressure difference with flow is directly proportional. So changes in pressure, an increase in it or a decrease in it, will cause the flow to increase or decrease. Like if the pressure decreases, this will decrease. For resistance, it's the opposite. Yeah, you're right. Repeat both. Which one? Both of these formulas? I don't mind. I can repeat. So, okay. There's no way to tell you how they came up with the formula, but I can explain how it makes sense. Okay. So for me, again, the flows. Okay. So flow of the blood through the blood vessel is determined, or it's affected by pressure difference and resistance. So pressure difference, again, like I said, if for example you have a higher pressure here and a lower pressure on the other end, the blood will obviously flow from greater to lower pressure because it's like forced to flow in that direction. Okay, the greater this pressure difference is, for example, you have 200 here instead of 100, it would flow even faster. So the greater the pressure difference between these two ends, the higher the flow of the blood. Okay, so greater, it will flow faster. That's just the formula. You would just put it, but I'm trying to explain how it happens. And then resistance. So resistance of a blood vessel is affected by things like how thick the blood vessel is, or how much it can push against that blood vessel, the blood flowing through it. So let's say you have a high resistance, like the blood vessel is very thick and very narrow to go through, you would have a lesser blood flow. So for high resistance, the flow would be less. That's why they're inversely proportional, I meant. So for something that's like weak, or it can allow blood to flow through, that's low resistance. It has a lower resistance and a greater blood flow. Does that make sense? Okay, I hope so. Okay, and then for the second formula. So as long as you memorize the formulas and they give you the values, you'll get the right answer. But I'm just trying to explain how the formulas came to be, like how the formulas make sense themselves. So the Reynolds number again. Okay, this number, this formula takes into account velocity of the blood. There's like density, and then there's viscosity. Do you guys know what viscosity is? Because viscosity just means how thick the blood is, like how thick it flows through. So yeah, viscosity, yeah, how resistant to flow. Yeah, that's also like resistance, but viscosity, for example, like it's like comparing honey to water. Honey is like very thick, yeah, very thick, right? Compared to water. Water is like more fluid. Fluid. I don't know. So the honey has more viscosity than water because it's more thick and it takes like it's very thick to like flow through. You get me? So the blood again, it depends on the fluid. So the blood can be less viscous, more viscous. It depends all on the amount of red blood cells it has. So let's say they have a lot of, if a blood vessel carries a lot of blood cells, red blood cells, it would be more viscous. Okay, and then if less, it would flow easily since there's less amount of red blood cells. So that's viscosity again. So I'll just write it like this so it's clear. Okay, so we just want you to memorize this formula if it like in case it comes. So again, Reynolds number depends on velocity, it depends on the viscosity and so on. So again, like I said, viscosity, if viscosity is high, if it's like very thick liquid, the Reynolds number would be less, right? It's inversely proportional, whatever is in the denominator. But what I want you to get at the end of all this formula is either you'll get a low Reynolds number or a high Reynolds number. So if you get a low, for example, 20, that's they'll give you a range, but low is, for example, 20, high is 200. Yeah. A low Reynolds number would indicate that you have laminar flow. So L, laminar. And then a high Reynolds number would mean you have turbulent flow in the blood. That's all what we want you to know from this slide. Is that clear for everyone? Should I move on?
So I have a question.
Yeah, sure.
If it is laminar, so less viscosity, right?
So laminar would have less Reynolds. Okay, yeah, wait. So if you write it down like that, if it's laminar, it means that you have a low Reynolds number. So what would happen to the viscosity, which is in the denominator?
Will decrease, right?
So wait. So in the denominator is always like inversely proportional to Reynolds. It's fine.
Oh, so it should big.
Yeah, increase. So it's like it's able to go through, you know?
Yeah, okay, I got it.
Okay. Do you guys have any more questions? Because I know this is probably the hardest, like the formula. So I'll move on if you guys don't have any questions. Do you want me to repeat it again? The last part? Okay, I'll move on. Okay. So laminar, this slide only shows how laminar flow is. So throughout a blood vessel, the blood would flow like this, right? The center, like the blood in the center of that blood vessel will be the fastest to go through because it has less resistance from the walls or from the nearby blood. Okay. Towards the end, it would go along the wall of the blood vessel, which means it has more it becomes slower in flow. That's why you'll see it like this. So the speed here is slower than the speed in the middle. Okay. The speed is the highest here. It goes way faster because it's less less friction is there. Is that fine? Because this is just extra. Okay. So again, this is the Reynolds number I was talking about. And it's mainly what we want you to know from this is that it's mainly dependent on velocity and viscosity. Now, whatever is in the numerator, it goes along with the Reynolds number, right? So let's say you have a high flowing blood, a high velocity, the blood flows at a very high speed. So the Reynolds number would be what? High or low?
Hi.
High, yeah. So what blood flow would that be? Laminar or turbulent?
Turbulent.
Yeah. So if you have a higher velocity, if the blood goes through faster, you would have more turbulence, which means the blood would just go in all directions because it's very fast. It doesn't have any control. Okay. Is that fine? And the opposite, same. If you have a lower velocity, if it goes slower, it would have a lower Reynolds number, and it would be laminar. That's it. This is not in your slides, by the way. This is like for you in case you want like more explanation for it. It shows you how velocity is related and viscosity. So viscosity means in this case here it says lower. So this viscosity would be lower in cases of anemia, or that just means you have less RBCs, red blood cells, or less hematocrit, which is a measurement. So it just means the same thing. They're less in red blood cells. So that means that the viscosity is lower, and then Reynolds would be higher, and you would get turbulent. Is that all clear for everyone? Okay. If you have any questions, again, feel free to ask me. This is just a picture of like how the red blood cells affect viscosity in the blood vessel. Now, again, so this law, the law that has all the equations about pressure, it's called wait, someone is asking, are these Dr. Peter's old slides? Yeah, because they are, right?
Yeah.
These slides, yeah, because that's how he taught it to us, and I want to think that I don't know, we can teach it in the same way he taught us, because that's how I remember. And okay, again, to continue. So there's, again, like I said, flow is again pressure over resistance, change in pressure over resistance. And this is called the bulk flow law. This says the same thing. P1 minus P2 is pressure difference. R is resistance. Here, it's over R. Okay, that's flow. And flow can be said, it's the same thing as saying cardiac output, because cardiac output is how much the heart works, how much blood is like leaving the heart. Okay, that's flow. And pressure difference, again, it came up before, right? The mean arterial pressure. The aortic pressure minus the right atrial pressure. But you don't need to worry about this. Just know this equation and you'll be fine. And resistance is again, sometimes they call resistance either like total peripheral resistance or systemic vascular resistance. They mean the same thing. If there's a resistance, you can use it in the formula. Like you just use it in the formula. So these two talk about, again, they're divided the formulas into systemic and pulmonary. I hope it doesn't confuse you because they're doing the same exact thing. They're using the same formula, but just in different words or in different variables. So for example, systemic, okay. What's the pressure difference in the systemic circulation? It's the MAP, right? We calculated it before. We said this is the body's pressure, like mean arterial pressure. So when you want to rearrange this formula, okay. If you have any questions, please stop me if I'm going too fast, okay? If you want to rearrange this for P to be like in the subject, you would want the pressure, the formula would be difference in pressure is equal to flow times resistance because you would move this here. Now for systemic, we said that the pressure difference is the same thing as saying body's pressure difference, MAP, mean arterial pressure. So they just replaced pressure difference with mean arterial pressure. For the blood flow, we said that the flow could be, it's the same thing as saying cardiac output, because cardiac output, again, is just how much the heart pumps out blood. And it's the same thing as saying flow. Resistance, they replaced a resistance with the words total peripheral resistance, TPR, or SVR. But if you see these, just know that they're the same exact thing. They're just taking resistance. So if you put this together in this form, you would have MAP is cardiac output times the systemic vascular resistance, because we're dealing with the systemic circulation. Okay, now if you go back, you would see that they wrote the same thing. So MAP is total, it's the same thing. So cardiac output times resistance, or they just rearranged it. But do you guys get this? Like how we got this? They just replaced the variables with their, like, in regards to systemic circulation. Is that fine? Do you guys have any questions? Do you want me to repeat? It's clear? Okay. Okay. Now they did the same thing for pulmonary, but they used, again, they used the pressure difference they used is the one we calculated, like M mean pulmonary arterial pressure minus the left arterial pressure. Okay, the one thing that's missing here, like the pressure difference, is that they didn't take so this is pressure difference, right? They didn't take right atrium, because we said the pressure difference is the body's pressure minus where it goes at the end, so right atrium. Okay, but right atrium is usually like 0. It doesn't make that much of a difference, because like we said, right atrium has the lowest pressure in the atrium. So that's why I think they crossed it out from here. But if you want to do pulmonary, okay, can someone help me with the pressure difference? Like, can you guys tell me what the pressure difference would be in pulmonary? So what's the pressure we call in the lungs? Like, what is it called? Which formula do you use to take it? Yeah, MAP, yeah. And you know how to calculate the MAP if they give you systolic and diastolic, right? What's the last place that the blood will go from the lungs?
Left atrium.
Yes, left atrium. Yeah. So that's the pressure difference in this formula. Okay, so when you want to calculate for pulmonary, you would do the MAP of the pulmonary, systolic and diastolic, and the left atrium as the endpoint. For the flow, again, you would take cardiac output. Just a second. Okay, cardiac output. And for the resistance, you would take the peripheral vascular resistance. Again, it means the same thing. They'll give you resistance. Now, when you want to rearrange this, you would have the pressure difference, which is MAP minus LA. We're just rearranging it into this, just putting these values. So cardiac output times the resistance. So this is the whole, like, this is the main law we're talking about. It's called bulk flow, because it calculates the flow of the blood, and we're just calculating systemic and for pulmonary, but we're just adding variables. Like for systemic, you would have a difference, like a pressure, right? It would be higher, much higher. So here, that's what they did for the pulmonary circulation. That's how they got the pressure difference over the resistance is CO, or flow. It's the same thing. If you rearrange it, it's the same thing. The one I calculated was from pressure, from pressure difference, from this one. The one I got was like this, but you can change it to this or this. Does this make sense? I'll keep this here if you want me to repeat it, okay? Should I move on, or is that fine with you? Okay, fine. So since we talked a lot about pressure, this is just a diagram I'd like to show you. So this is what I meant, the pressure difference from one end to the other. And these are the old slides as well, because I know I found them more clear. So this is the formula we were talking about this whole time. It's just rearranged into this, it's rearranged into resistance. Okay, so the main concept from this is this formula we want you to understand, and we want you to apply it to systemic or pulmonary. Now the pressure gradient with the flow, they are something that can be measured, but resistance, you can't really calculate like how resistant a blood vessel is. Okay, so it's something that should be calculated. So you can calculate resistance by another formula, which is this. Now resistance, they came up with this formula. I mean, I don't know, you have to memorize it, but it also makes sense because length, like how long the vessel is, affects resistance. How wide the vessel is, this is radius. How wide the vessel is also affects resistance. So whenever you see small r, that's radius. If it's big R, that's resistance. Okay, now radius, so from all these values, changing which variable, changing which one of these would have the greatest effect on resistance. So what should you change to like affect the resistance the most from the numbers? So it's either L, yeah, radius. So why radius? Because it's R to the power of 4. So even if you have even if the blood vessel is very small, if it's 2, for example, and if it gets changed to 4, it would be to the power of 4. So imagine how big value that would be. So that would affect the resistance the most, and inversely proportional, because again, it's in the denominator. So let's say the blood vessel is like this big and it has a very, very large radius. So would the resistance be less or higher?
Less.
Yeah, bigger radius, less resistance. That's all I want you to know from this one. And this is important because it comes up in the other law, which is Poiseuille's law. Again, it has to do with flow. Now, again, like I said, in a normal situation, you cannot measure resistance. So what would you do? You would measure things like length, you would measure radius to get resistance, right? So they made a formula from the resistance formula and the flow formula to like come up with this equation under something called the Poiseuille's law. Okay, so we'll try to explain it again. So what was the flow equation? It's this one. This is the main equation for flow. Okay, since resistance can't be calculated, like can't be measured, you can insert this formula in place of resistance. That's what they did here. That's all they did. So this is the second formula I talked to you about to calculate resistance, right? So what they did is they just combined this into here. So you can they can measure flow like really well. So okay, so here it's pressure difference over resistance, big R. So this just means if you put pressure difference times 1 over R, because it's the same thing as putting pressure difference over R. It's the same thing multiplying 1 over R. Now 1 over R just means you take, so what did we say R was? R was this times length over R to the power of 4. Okay, with of course with the number 8. Yeah, no wait, it's here up. Wait, I'll repeat it again. So because it's okay again. So this is the first formula we talked about. This is the resistance formula. Okay, we want to replace this formula in here. This, just saying this is the same thing as saying this. So you want to multiply 1 over R. It's the same thing as saying pressure over R, pressure difference over R. Okay. Now you want to have resistance here. So in this slide, what they did was they removed the constants like away, so you can only deal with this for now. Also, you don't need to know how the formula was derived. I'm just trying to make it easier for you. So you want to replace this one here. So you would have this one would be viscosity times length over radius to the power of 4. Since this is 1 over this, it means you flip it. So 1 over this means you're taking the inverse of the formula. The easiest way to do that is you switch this with this. So r radius to the power of 4 over pi viscosity times length would be 1 over r. This is 1 over r. Okay. Don't call me doctor. I don't know who that is. But anyways, 1 over r is here. Okay, so you replace this with this. Now, this one you would put in place of 1 over r and multiply it by pressure difference times the constants. It's the same thing. The constants, they just removed this they just removed this aside because they would never change either way. But you can see here they're flipped, right? So here it was 8 over pi, but here it's pi over 8 because, as we said, we want to take the inverse. So we want to take 1 over it. So the easiest way to do that is you flip. Now, once you put all of this together, you'll get this law and this formula, which is flow is pi times pressure difference times radius to the power of 4 over 8 times viscosity times length. All what they did is they replaced r with this formula, with this formula. That's it. Is that clear for everyone? Because yeah, again, this is one of the important ones. If you want me to repeat, I can go over it again. Did I?
Dr. Momo.
I don't know. Did I repeat it? I really don't mind. It's clear? Okay. Okay. So all what they did again was they replaced r with that formula and they got this. So as long as you know that, you're good. So pi over 8 will never change. Pressure difference, they might give you values. Radius will change. And I doubt, like, they never got us questions for length or viscosity, but they're in the formula. So you would know how they change with the, like, how flow would change. Now, so here again, like I said, resistance is mainly dependent on radius. Just because it's to the power of 4, it affects it so much more. Okay, as a summary, the main formula that gives rise to all of these formulas is flow is pressure difference over resistance. I'm sorry, resistance. Now, flow can be substituted with cardiac output, like I said, because cardiac output is flow. It determines the flow of blood. Pressure is the MAP that we calculated in the first slide. And then resistance, it's also called TPR, total peripheral resistance. All the sum of all the resistance. Now you can rewrite this equation. The cardiac output is mean arterial pressure divided by resistance into this. It's the same exact thing. And we did this for systemic, if you remember, and pulmonary. No, I'm almost done. I promise I'm almost done. But I hope that was all clear. I'll move on to resistance. Like I said, resistance this is like the easiest part of this lecture, the one with resistance. So let's say you have a blood vessel. You have like this blood vessel, like a lot of blood vessels together, right? And you want to know what's the total resistance. Now you're forgetting about, so let's say they're all the same length, there's the same radius, you don't care about that formula anymore. You just want the total resistance in this line of blood vessels. So you would have resistance 1 of this, resistance 2, 3, 4, 5. Okay, if they're in series, if the blood vessel is like continuous, it's in series, you would just add them up. So you would do the total resistance and you just add R1 plus R2 plus R3, R4. That's easy, right? Because, yeah, is that fine? For C, if they ask you resistance in series, you just add the numbers up, whatever you see. Okay. Now we'll move on to questions. I forgot question. So
This
some
is
can,
easy.
yeah, it's very easy. I just said it, but can someone calculate the total resistance of this?
130.
Yes.
Good. Sorry.
Yeah, it's okay. It's okay. Yep. Now we'll move on to parallel. I hope that was clear for everyone. So for parallel, it's a bit complicated, but again, it's easier than any of the other formulas. So for parallel, since like they're in different pathways, right? So you can't just add them up. It won't give you a correct answer. So you would want to calculate the resistance of vessels in parallel. You would do 1 over the total resistance. That's just how the formula is. 1 over total resistance is equal to, you would add 1 over R1, then 1 over R2, then 1 over R3, and you would just keep on adding. The only difference between series and parallel is that you do 1 over it. Okay. And then, so you would just add these, like all of this. These all values would give you 1 over, so all of these values will give you 1 over the total resistance. Now, I don't want you to forget that this is 1 over total resistance. So the total resistance, if you want to calculate only this part, it would be 1 over the whole thing. So you would do inverse. So I'll give you an example. So for example, let's say this is 10. Let's say all of these are 10. You can't just add them up. So you would do 1 over 10 plus 1 over 10 plus 1 over 10. Okay. And then it would be 3, or that would be 3 over 10. Now, is this the total resistance? No, because the formula said, like the whole formula is 1 over total.
What? Someone's saying flip it.
Yeah, exactly. So you want the inverse of this. So you would flip. The easiest way to do that again is you flip it. So the total resistance would be 10 over 3. Okay, is that fine? So just don't forget to flip it in the end after you add all the 1 over. Is that fine with everyone? Because there's one more formula after this, and then I'm done. Okay, so this is just for you to know. Let's say there's 5, there's 10, there's 20 in parallel blood vessels. Okay, the total resistance would always be less than the least resistance in this one. So in this case, the least one here is 5, right? So the total resistance of all of this the answer would always be less than this value, less than 5. So let's say you have 6, you have 4, you have 3 in parallel vessels. The answer would always be less than the least one, so less than 3. So that's how, if you get a larger value, then you know that there's something wrong, or you forgot to flip, for example. Okay, this is just for you. Just for Question. Can you guys calculate it real quick? Because the formula is in the previous slide.
They don't have these ones in their slides, right?
Oh, we'll send these slides, by the way. We'll
Yeah, I'm
send.
asking. They don't know the
No.
answer to this. I don't remember where we got this from.
Is it 4?
Yeah.
Yeah.
No. Okay. So you would do just so whoever's like watching this, so you would do 1 over 5 plus 1 over 25 plus 1 over 100 is 1 over the total resistance, right? Yeah, I'll do it. So this one, it would be like you would make it the same denominator. We have 4.
No.
No.
First one is not 4. The second one's 4.
Yeah. Wait, yeah, you would make it to the biggest denominator, which is 100. So 5 times 100 divided by 5 is 20. So this would be 20 over 100.
Sorry.
And then 4 over 100, and then 1 over 100. Now, when you add this up, it will be 25 over 100. And when you flip this, it would be, because this is the formula, you would have 100 over 25, which is 4. Okay. I hope that's clear. Because there's one more thing. Oh,
No. Sorry.
I'm
This
sorry
is
for taking
the
too long.
style of question that you're likely
This-
going to
yeah.
get on your exam. We're combining those two concepts in one now.
Do you guys want to try solving this? Because you guys can try. We can wait. So all the values are here. this is in parallel, and these are the ones in series. This is 5, this is 7. Take your time, you can calculate it.
What? Huh? It's fine. Okay.
I hope you're calculating.
So give time for people on the
I
recording.
got 14.22.
Yeah, yeah, that's the answer. So, should I do it? Yeah.
Yeah. Well, did everyone get how?
Did everyone get how I got it? Because we'll write it in the notes how I did, and you can like you can try doing it yourself. Okay, because the basic idea is that this is in parallel, so you would go like you would flip this value and you just add 5 and 7 to it. That's all. Okay.
Is that clear?
Is that clear?
Can you do it again?
Okay, yeah, sure.
Just do the whole thing.
Yeah, I'll do the whole thing for this question, right?
Yes.
Okay.
Yes.
So so let's start with the parallel first. That's how I would do it. So A is here. Here is 5. B is 7, and then you want the total of this, so you can add it to this and this. So okay, let's do it. 1 over the total resistance. Since it's parallel, you would use this. So you would have 10, 10, 5, and 20.
Mhm.
So you would do 10, 1 over 10, 1 over 5, and then 1 over 20. Okay. Now, once you add this, so to add this, you would need the same denominator. So you would want to multiply this by 4. You would want to multiply this by 2. And then you would want to multiply this by 2 so that they're all 20 and you can add them all easily. So this would be 2 over 20 plus 2 over 20 plus 4 over 20 plus 1 over 20. Now this would be equal to, wait, 4, 5, 6, 9 over 20. Okay. And this is just 1 over the total resistance. So the total resistance would be you flipping them. So total resistance would be 20 over 9. Does that make sense so far? Like, is the step?
Yes, I got, yeah.
So 20 over 9 is, so this is the total of this parallel circuit. So 2.2. So 2.2 plus 5 plus 7, you would get 14.22. Is that fine?
Don't distract them. They're doing equation.
Yes. Thank you so
Okay,
much.
you got it? Okay.
Yeah.
No problem. Now the last part of this lecture is it's just about cardiac output. So cardiac output again is like flow, right? How much the blood is pumped out of the heart. Now there are ways to measure it. You can calculate it too. There's a way you can measure it by echocardiography. You don't need to know this. I think he just put this for extra information, but echocardiography, it's just how, like, it's a method. It's a way you can see the heart, like, chambers, okay, how big or small it is. And by that, they can measure cardiac output. But we don't want you to know that. They want you to know this formula. Oh, what happened with the slides? Can you guys see the slides?
No,
No.
Sorry.
there's only one Ibrahim.
Oh,
Or
one
two.
second. I'll rejoin the thing
Yeah,
from
yeah.
here. Oopsie.
Sorry. Okay, so this, like, the last formula is cardiac output. It's to calculate cardiac output.
It looks like I'm doing it.
Sorry.
Share. Can you make this one host again?
Yeah.
Okay.
Okay.
There we go.
Can you
Can you
see it?
now?
No.
Why not?
Oh wait, I'm so sorry. By the way, wait.
says it's on.
Okay,
Here we
that's
go. Okay.
okay, can you see it now?
Yes.
Okay, sorry. So like I said, cardiac output is calculated. It can be calculated, and that's what we want you to know from this slide. So the equation they have is based on oxygen and how much the lung can, or how much the lung can give oxygen to the blood. And that's kind of a measurement for cardiac output, because it's how much oxygen it can carry in like one cycle. So this is this is an alveoli from the lung, and oxygen is coming in. This is the blood vessel, right? So the whole formula is the amount of oxygen in the numerator over the oxygen amount in the arterial side, meaning the oxygen amount after the blood passed through the lung, minus the oxygen amount in the veins. So the blood vessel bringing it. So again, the blood carrying oxygen is Ca. Okay, it's just oxygen content of the blood per milliliter from the lungs. It's coming out of the lungs. Cv is from the veins. It's going to the lungs to get the oxygen. So the oxygen amount here would be low, and then Ca would have higher amount of oxygen. Now, the third variable is the amount of oxygen that comes in when we breathe, right? So that's in the numerator. So do you guys get that? Do you guys get all the variables? The important thing of this is the formula itself and the unit. So we want you to always calculate it in per milliliter. Is that fine? Because I'll give you an example of this again after this. So so let's say this is 100, okay, and the blood coming in from the heart to the lungs is 0, because it has no oxygen, I guess. And then the blood coming out of the oxygen has around like 50. Because obviously that's why we're calculating cardiac output, because it can't take all the oxygen that comes in our bodies. It will only take some of it. So cardiac output is, again, you would put 100 over artery minus the venous side. So 50 minus 0. So it would be 100 over 50, and then the cardiac output would be 2, because this is the answer from here. That's an easy way you can calculate cardiac output, rather than like measuring it from this. Is this clear for everyone? Okay.
Yes, thank you.
Okay. So just don't forget the unit per milliliter when you calculate it. So that's it for hemodynamics 1. I don't know why there is a question, but okay, I'll add it in. I forgot to add this law in the updated one. Yeah, in the updated one, there's the formula for the Poiseuille's law, but this is basically all of the formulas under the name of the law, or the value you're getting, because they can ask you what's the the name, okay, with the formulas. This is just a summary. There's a question. If you want, if anyone can answer, go ahead. You can take your time, because this is the last slide of my lecture, and then he'll continue. His part is easier.
It's way easier.
It's so much easier. Mine has like all the formulas. I'll put it as you guys.
Give your answer in
milliliters.
1.5.
1.5 liters.
Yes.
Yeah.
Yeah.
Yeah, I think so.
Okay. Yeah. You're right.
Yes.
Don't worry. So this is I'll calculate it for everyone here. So this is the oxygen saturation, over the oxygen content in the arteries minus the vein. Okay. So the first thing you want to check is the unit. So here it's over 100 mil, right? We said we wanted only milliliter. So this would 20 over 100 is 0.2 milliliter. And then you would change this. You would say 40 over 100 is what? 0.4 milliliters. And then you would say this is this is 300. It's not over 100. So this is 300 milliliters. Now the oxygen consumption is this. So you would put 300 over the arterial oxygen is 0.4 minus, this is the venous 0.2. So it would be 300 over 0.2 milliliters. And when you calculate that, you would get 1,500 milliliters. When you want to change it to liters, or liters, you would divide it by 1,000 because milliliter to liter is divided by 1,000. So 1.5 liters. You can give your answer in either way, just make sure you have the right unit, okay? Is that clear? Do you guys have any more questions for me before I leave?
Let's go to the
Here we go. Okay, I hope that was clear. Yeah, this is the checkpoint. Do you guys want a 10-minute break? I wanted
think
to
we
ask.
should do
Yeah,
a 10-minute break.
because I know it's a
Are we
lot.
all in agreement for that before I start? We could get started right away to finish, but you guys just took a lot of information at once. Let's
Okay.
take a break. Okay,
fine.
so we'll come back at 8:45.
Yeah.
8:45 we'll be back, okay?
Thank you guys
And
for
then
listening.
Shahad, thank you. You can stop the
Yeah.